Okay, and then the next two videos are going to look at sketching quadratic graphs. Firstly, when the equation is given in turning point form, and secondly, when it is not given in turning point form. And these two videos will mark the end of the point where we are essentially treating all of this content as assumed knowledge. So you'll have a couple of weeks, 2 to 3 weeks of term to review, revise, brush up on this assumed knowledge content, at which point we'll do a common test, and then after that point we'll review some of the bit trickier quadratic stuff again before we finish off the quadratics chapter. Okay, so here we want to have a look at sketching graphs of quadratics given in turning point form. So all quadratic graphs form the same basic shape that's called a parabola. So to be really clear about that, students don't make that distinction. The parabola is the name of the shape, in the same way that that is called a circle and that is called a triangle, that is called a parabola. The equation is a quadratic equation or a quadratic function. Okay, so it's a quadratic function and the shape of that is a parabola. A parabola is a symmetric shape. The line about which the parabola is symmetrical is called the axis of symmetry. It's not a key feature of the graph. It's not something you should be drawing on the graph unless the question specifically instructs you to do so. The parabola has a turning point or a vertex, and the minimum or maximum value of y occurs at the turning point. So the example on the left over here, we have a maximum turning point. That is the maximum y value on that parabola. It doesn't get any higher than that, sorry, y value. This graph here on the right has a minimum turning point. That is the minimum y value. Okay, and that's important when we start to look at application problems. When you sketch a parabola, it's important that it reflects that you understand that it's a symmetric shape. So you must have a smooth, symmetric, parabolic shape. If you don't, erase it and draw it again, which is why you should draw it with a pencil. So far we've considered the algebra of quadratics in this polynomial form, but it's easiest to graph quadratics when they're expressed in turning point form. Y equals a times x minus h all squared plus k. And actually the algebra in that form is also easier because it is a quadratic with just one x in it and it can be solved by rearrangement. So actually the easiest way to work with quadratics, both the algebra of them and the sketching of them, is when the equation is given to us in turning point form. If we want to go from this polynomial or expanded or general form to turning point form, we need to complete the square. And we'll review that in a couple of videos' time. But for now, we're not going to be asking you to complete the square. We're going to, if we're given it in this form, we'll look at how we can sketch it in this form without completing the square. If we're given it in this form, we'll do what we're going to do here in this video. Okay, so graphs of the form y equals a times x minus h all squared are formed by transforming or applying transformations to the graph of y equals x squared. I've summarized those transformations in this table. I'm just going to pause the video for a minute and change over to a graphing program where we can just explore those a little before we move on. Okay, so for now when we're looking at transformations of graphs, we're really just identifying patterns by looking at what happens to the graph and drawing assumptions from that. In Year 12, we'll delve much more deeply into the transformations of graphs and the algebra behind that, and why sometimes, things look a little bit backwards to what they should, particularly when we're doing transformations left and right. It seems a bit backwards to what it should. Dilations from the y-axis, when we get to those down the track, seems a bit backwards from what it should be, and we'll be able to understand a bit more clearly from the algebra about why that sort of eventuates. But for this year, we really just want to establish the patterns by looking at different graphs and then draw conclusions from that. So here I've got the graph of y equals a times x minus h all squared plus k drawn here, but at the moment a is 1, h is 0 and k is 0, and so this is just the graph of y equals x squared. Let's focus just on a first of all. So as I increase the value of a, so I've now increased the value of a to 1.1. I've kept that black line is still going to be y equals x squared, so we've got that point of reference, 1.2, 1.3, 1.4. And what a lot of students talk about is they talk about the graph getting thinner, the parabola gets thinner. But actually that's not very helpful in you understanding the maths of what's happening here, okay? So let me go back to perhaps, let's go to maybe a is 3, for example. So what's actually happening here, and I can draw in this program, but it's very poor, so excuse the drawing. The original graph went through the point 1, 1. The dilated graph goes through the point 1, 3. What's actually happening is we're multiplying, sorry I can't write 3 there, that's a 3, we're multiplying the y values by 3. This point that was at 2, 4 is now going to be up off the charts out here at 2, 12 because we'll have multiplied the y value by 3. So it's a stretch in this direction. All the y values are being tripled. Not so much, it's better to think about it that way rather than a squash in that way, okay? So thinking about it as a stretch rather than a squash. Okay, let me just remove all those annotations. Okay, so we talk about that as a dilation. So the formal word we want to be able to use is dilation rather than stretching and squashing. It's a dilation by a factor of 3 away from the x-axis. So in this direction is the stretch, okay? So dilation by a factor of 3 from the x-axis. So that's because a is 3. If we made a 2, oh sorry, why is it changing k? If we made a 2, sorry, go down. It's a dilation by a factor of 2 from the x-axis. If we made a decimal, let's say 0.5, it's a dilation by a factor of 0.5 from the x-axis. So all the y values have been halved, which makes the graph closer to the x-axis. Rather than thinking about it having gone wider, so rather than thinking about that having happened, what we want to be able to think about right back there, is that what's actually happened is that the y value here got multiplied by half, okay, times 0.5. We've halved. So it's still all about this direction, it's not about this direction, okay? Okay, if we keep making, changing back to k, if we keep making a negative, sorry, back to k again, come back to k, we've got a clear idea of what's happening with k. If we keep making a smaller and smaller and smaller, eventually a will become 0, which is that's just the line y equals 0, so it's not a parabola at all. So a has to be something other than 0. But if we make a negative, our graph now goes down here. And it's still the same thing. The y values have now been multiplied by -1. So the graph has ended up, you take that y value, you multiply it by -1, it ends up down there. You take that y value, you multiply it by -1, it ends up down there. Okay? So we've multiplied all the y values by -1, which has the impact of reflecting the graph in the x-axis. Okay? So if a is -2, there are two things happening to the graph, two transformations. The negative has resulted in a reflection in the x-axis. So the x-axis, thinking about the x-axis as the mirror line, and the 2 has dilated the graph by a factor of 2 from the x-axis. You can think about those, they can happen in either order. It might have been dilated by a factor of 2 first and then reflected in the x-axis, or it could have been reflected in the x-axis and then dilated by a factor of 2. Those two transformations, the dilations and reflections in the x-axis, they can happen in any order and they still have the same impact. There are other combinations of transformations where if we do them in different orders, we get a different result. Okay, so it's important to think about order. So when we're when we're looking at a parabola in this turning point form, the first thing that's happening to the parabola is the dilation and the reflection caused by A. Let's put A back to 1. And then after that, it's the transformations that are caused by H and K. So let's leave A at 1 now. Let's have a look at H. Actually, let's go straight to K because we've been seeing that repeatedly, accidentally, and it's actually the easier one. So K, as I make K bigger, the graph is simply translating up. Some people get confused because it can start to look like it's sort of dilated, but it's actually not if you just look at the vertical shift. Wherever you choose, if you just look vertically, it's gone up by the exact same amount. Okay, the whole way along the graph, it's increased by the same value. And in this case, it's gone up by 2.7 units because K is currently 2.7. All right, so as we add to K, it goes up. So as K gets bigger, the graph translates up. So if it was plus 10, it would translate up by 10. If K is negative, so if it's minus, minus 3 there, the graph has translated down by 3. So we just directly translate the graph down by 3. So we're not multiplying the y values for anything. What's happening is we're subtracting from the y values. We've subtracted 4 from every y value, and we've ended up translating the graph down by 4. Okay, let's put k back up to 0 again. 8a is still 1, and let's have a look at h. So we've set up the equation so that it is x minus h all squared, and what we'll find in this form is as we make h bigger, the graph goes to the right. So when the equation, but it's important to think about what this is what's happening in the equation here. So when the h is 2, the equation is x minus 2 all squared, and the graph has gone to the right by 2. So minus a number makes the graph go to the right when it's inside of that bracket. And then if we were to make h a negative value, so here h is negative 1. If we think about putting h equals negative 1 into that general form of the equation, that's x minus minus 1, so that's x plus 1 all squared, and the graph has gone to the left by 1. Okay. If it was x, plus 2 all squared, it would have gone to the left by 2. And then obviously we can put all of those things together. We can have, different h, different k, different a, and we get all our variations of possible parabolas. Okay. All right, let's go back over to the notes and have a look at that summarized and then sketch some parabolas. Okay, so we've got our 4 possible transformations. 2 of them are connected to A. They're the first 2 things that happen to the graph. So the magnitude or size of A dilates the graph by a factor of A from the x-axis, so stretches it up or down. The sign of A, if A is negative, then the graph is reflected in the x-axis. The value of h translates the graph left or right. For example, x plus 1 all squared is x squared translated 1 unit to the left, and x minus 3 all squared is x squared translated 3 units to the right. And k translates the graph up or down, and it's a more direct translation. So x squared plus 2 is x squared translated 2 units up. X squared minus 5 is x squared translated 5 units down. Identifying these transformations so we know what our parabola looks like, along with then calculating any x or y intercepts, allow for the easy sketching of our quadratics. Okay, let's do some examples. So sketch the graph of y equals negative half x squared plus 4. Okay, so it's important that we understand that this is in turning point form. This is negative half times x minus 0 all squared plus 4. So it hasn't translated to the left or right. It has translated up or down. It's reflected in the x-axis, and it's dilated by half from the x-axis. Okay, so what we have here is reflection in x-axis, dilation by half from x-axis, no translation up or, left or right, but translation up by 4, which means that the turning point, which for y equals x squared is at 0, 0, if we translate up by 4, the turning point is now at 0, 4. Okay, so we can picture what that graph looks like. So it's gone up by 4, but it's reflected. So turning point's at 0, 4, but it's going to go this way. So it will cross the x-axis. So x-axis, sorry. So we want to calculate those x-intercepts. This is actually the y-intercept. Okay, it's also the y-intercept there. So we just need the x-intercepts. And when we've got an equation in turning point form, which we have, we can always simply solve just by rearranging. So I'm going to, because I don't like the negative in front of the x squared, I'm going to add that half x squared, that half x squared to both sides. So we get half x squared equals 4. Now I'm going to multiply both sides by 2 to counteract the half. So to get rid of the half, we're multiplying both sides by 2, so x squared equals 8. And then x is going to be plus or minus square root of 8. 8 is 4 times 2, so square root of 4 times square root of 2 is 2 root 2. Simplified so. Okay, so again, draw your axes after you've done your calculations. This is 0, 4. This is 2 root 2, 0. This is negative 2 root 2, 0. X and Y. So your reflection is important. Your dilation doesn't really affect how you're going to draw the graph because that will come into things with the calculations. So if it hadn't been dilated, these x-intercepts would be further out. Okay, so when you find your intercepts, that will take care of being able to show the dilation in the graph. It's really important that minimum information for your quadratic should be the turning point and at least one other point. So if your turning point is at the origin, and so your turning point and your axis intercepts are all the same things, you do need to mark an additional point. But you must also have all x and y intercepts labelled, so you often end up with more than that information labelled. Okay, let's have a sketch of this graph. Y equals x minus 3 all squared plus 1. Okay, so A is just 1, which means dilation by a factor of 1 from the x-axis is no dilation and no reflection. So all we've got is this minus 3, which is a translation to the right by 3, and this minus 1, which is a translation down by 1. So we're translating right 3 and down 1, which means the turning point goes from the origin right by 3 and down by 1, so it's going to be at 3, 1. Okay. Alright, so immediately you want to think about, so we know our turning point, no reflection, turning point over here, so we will cross the x-axis. Okay, so sometimes a graph, if it had been reflected in the x-axis with its turning point at 3, sorry, that's 3, negative 1, at 3, negative 1, it wouldn't have x-intercepts, so you wouldn't bother trying to find them. Okay, so it's important that you do a bit of thinking about the reflection or not and where the turning point is as to whether your graph will cross the x and y x-axis. It will always cross the y-axis. Let's work out our y-intercept. So again, it's not the number on the end, it is what you get. What does y equal when x is equal to 0? So that's negative 3 squared minus 1. Negative 3 squared is positive 9 minus 1, so that's 8. So 0, 8 for the y-intercept. And the x-intercepts, again, because it's in turning point form, we can just solve by rearrangement. So it's 0 equals x minus 3 all squared minus 1. So here's the x here, we want to get it on its own. To construct it, we've subtracted 3 from x, then it's been squared, then we've subtracted 1. So we're going to add 1 to both sides first. We want to undo those things in the reverse order. We're then going to take the square root, plus minus root 1. Square root of 1 is 1. The number of students who leave root 1 in solutions baffles me. 1 squared is 1, so the square root of 1 is 1. And so x is going to be 3 plus or minus 1. And we're not going to write 3 plus or minus 1 because we know what 3 plus 1 is. It's 4, and 3 minus 1 is 2. Okay, so there's our x-intercepts at 2, 0 and 4, 0. Okay, so let's think about what we've got. 3, negative 1, we need quite relatively big y-axis intercept. Given that you've got more than just one point happening on the y, so we could put 3, negative 1 here, but then you don't want to put, you don't want this to be 3 and this to be 2 here. You want some consistency. So I am going to just plot out a bit of a scale. Okay, so let's go with 1, 2, 3, 4. And then I'm also going to go with the scale this way because I want negative 1 up to 8. So I want to get that vaguely accurate. Negative 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we want to cross the y-axis here. Our turning point is going to be here. We're going to cross through the axes here and here. It can help to then think about that nice symmetric point up here, just to give you somewhere to kind of aim for when you're drawing your shape, to help give you a symmetric shape. And again, because we're trying to hit key points, it can be hard to get the shape right, so do it in pencil, adjust it if you need. Try not to get it looking too straight, try and have some curvature to it. I did better on the right hand side than on the left. Alright, so that's the point 4, 0, that's the point 3, negative 1, that's the turning point, we need that. That's another x-intercept, 2, 0, we need that. And that's the y-intercept, we need that. Okay, and there's our graph. Example 3, the final example. Sketch the graph of y equals 2 times x plus 1 all squared plus 5. Okay, so there's no reflection. We've got dilation by a factor of 2 from the x-axis, so that's not really going to affect how we draw it. We've got translation, so this plus 1 is to the left by 1, and this plus 5 is up by 5, which means that our turning point has coordinates of -1, 5. And if our turning point is at -1, 5, and we've not got any reflection, it's not going to cross the x-axis, so we're not going to calculate x-intercepts at all. We just need to work out our y-intercept. Let x equal 0, 2 times 0 plus 1 all squared plus 5. So that's 2 times 1 squared plus 5. 1 squared is 1, so it's just 2 plus 5, which is 7. So 0, 7. Okay, so thinking about our axes. 1, 2, 3, 4, 5, 6, 7. So let's have -1, 5 there. We're going to cross the axis there at 7. So let's mark a symmetric point sort of here to help us get the shape right. Zero, 7. And there's our graph. Minimum information, turning point, and one other point. So we've got that. And that's all we need. Okay, so some practice sketching graphs given in turning point form in exercise 3D.